Hi, I'm Dr. Incognito. In this video, we're going to examine properties of the determinant. Properties of the determinant. So first, suppose we have a matrix that has either a row or column of zeros. So 1, 2, 0, 3, 4, 0, 5, 6, 0. If there's a row or column of zeros, then the determinant of the matrix is going to be 0. Because you could do a Laplace expansion along the 0 row or the 0 column. And so every term in the expansion will have a factor of 0. And so the sum will be 0. So if a matrix has a row or column of zeros, the determinant of that matrix is 0. Also, if a matrix 1, 2, 3, 1, 2, 3, 4, 5, 6, if a matrix has two equal rows, two or more equal rows, then in this case, the determinant is also 0. The determinant will be 0. That's not as obvious in the 3 by 3 case as it is in the 2 by 2 case. If there's two equal rows, AB, AB, then the determinant here is going to be AB minus AB, which is 0. So if the determinant, if the matrix has two equal rows, then the determinant will be 0. If the matrix is triangular, if A is an n by n upper or lower triangular matrix, then the determinant of A is the product of the diagonal entries. The product of the diagonal entries. So for example, if A was the matrix 1, 2, 3, 0, 4, 5, 0, 0, 6, then the determinant of A, this is upper triangular. Upper triangular meaning that below the main diagonal are only zeros. Lower triangular would mean that above the main diagonal there's only zeros. So the determinant of A is the product of the diagonal entries. 1 times 4 times 6, which is 24. And a very important special case is the identity matrix. I'll write the 3 by 3 matrix, but for any size, the identity matrix is both upper triangular and lower triangular. It is a diagonal matrix. And the determinant of the identity is 1 times 1 times 1. So the determinant of the identity matrix is 1. A major property is that the determinant of a product of two matrices is the product of the determinants. And this is not an obvious property at all, but it is a very powerful property. The determinant of a product is the product of the determinants. And for one thing, if your matrix A has an inverse, so if A is non-singular, it has an inverse, then the determinant of A inverse is 1 over the determinant of A. And that's because A times A inverse is the identity, and then the determinant of A times A inverse is therefore 1, because the identity has determinant 1, but also this is equal to the determinant of A times the determinant of A inverse. So the determinant of A times the determinant of A inverse is 1, and therefore the determinant of A inverse is the reciprocal of the determinant of A. A couple of other properties. the determinant of A transpose is equal to the determinant of A. This is not obvious, but in the 2 by 2 case, it's pretty clear. If A is A, B, C, D, then the determinant of A is A, D minus B, C. And then if you look at A transpose, that would be A, B written down as a column and C, D as the other column. And the determinant of A transpose, it's AD minus BC. So they're exactly the same. The determinant of the transpose is equal to the determinant of the original matrix. And the last property, if you multiply a matrix by a constant, then that affects the determinant. So if C is a scalar and A is an n by n matrix, so A is n by n, and that's very important here because n is going to play a role in this formula. So the size of the matrix matters here. The determinant of C times A is going to be C to the power n times the determinant of A. So if A is a 4 by 4 matrix, and the determinant of A is -3, then the determinant of 2A will be 2 to the 4th times -3, which would be 16 times -3, and that's -48. So the determinant of a multiple of a matrix is 2 to the power, or the multiple to the power of the size of the matrix times the determinant of the original matrix. Okay, so there are some properties of the determinant. Thank you for watching.